thank you all for being here, and for having me, for inviting me, for having me today. It's really a pleasure and an honor to be here today in front of you, even if only remotely. Okay, so today my talk is about correlation clustering, and in particular some latest advances about correlation clustering. So first of all, let me just give credits to the people who worked with me on these topics, who are Lucio Lacava, Domenico Mandaio, and Andrea Tagarelli from the University of Calabria in Italy. So they are all co-authors of the papers which I'm gonna tell you about today. Okay, this is a short outline of the talk. I will give you first of all, some background about correlation clustering. Then basically, I will talk about three topics about correlation clustering. I hopefully will be able to cover all the three topics, but at least the first two. Let's see if the third one, maybe I will give you just some hints, but let's see. So the first one is about correlation clustering with global weight bounds. Then I will switch to a reinforcement learning formulation of correlation clustering, particular within the combinatorial multi-armed bandit framework. And then I will talk about how correlation clustering can be basically contextualized within a context of fairness, so fair clustering. So, okay, first topic, correlation clustering with global weight bounds. So first of all, let me just move. Okay, otherwise I don't see the slides. Sorry. Okay. So first of all, background on correlation clustering. So clustering in general is a well-established data-mining task, where the goal is to group a set of objects so that similar objects are put as much as possible within the same group, within the same cluster, and the dissimilar objects are put in different clusters. There are many formulations of clustering. This is one particular formulation. Correlation clustering is one particular formulation of clustering, which is quite appealing because it is perhaps one of the most natural formulations of clusterings. It also have some other appealing properties because algorithms for optimizing this formulation basically don't need to have the number of clusters defined up front. There are several theoretical results about correlation clustering, which guarantees that the algorithms that are used for this particular formulation are grounded by theory, and also they are actually proved to be effective in terms of both effectiveness and efficiency. So this is quite nice for formulation of clustering. And how is it this formulation? So basically you are given a graph which can be complete or not. So the vertices, the nodes of the graph are the objects to be clustered, and the edges are the relationships between the objects. There can be a relationship, so an edge for every pair of nodes. In that case, the graph is complete. Otherwise, the graph may also be not complete, maybe sparse. For every edge, we have two types of weights assigned to every edge, which is a positive type weight, which is denoted as a plus, as here in the notation. So WUV plus is the positive type weight assigned to the edge between nodes U and V, and a negative type weight assigned to the same edge between U and V. So what's the rationale of these two two weights. So the positive type weights somehow expresses the benefit of clustering U and V together, while the negative type weight expresses the benefit of not clustering the two vertices, the two nodes together. So given these two weights, the correlation clustering, the optimization problem underlying formulation of correlation clustering, and in particular the one that is called mean disagreement correlation clustering, is the one here. So basically for every edge in the graph, and such that for every edge UV in the graph such that U and V belongs to the same cluster, we compute the sum of the negative weights. So we want to minimize the sum of the negative type weights, plus the sum of the positive weights that are computed on the edges between objects in different clusters. So the idea is that within a cluster, so with the first term, basically we capture the fact that within a cluster we want to observe a sum of negative type weights which is as small as possible, because we don't want ideally edges with high negative type weights, and the other way around, the opposite for the edges placed between vertices that are in different clusters. Okay. So the special so this is a formulation of correlation clustering which is called mean disagreement. There exists a counterpart of correlation clustering, of a correlation clustering formulation, which is called max agreement, but it's less appealing because it's less tractable from a theoretical point of view. So the focus here in all the papers and in general in the literature about correlation clustering is about this specific formulation, this minimization formulation. Okay, but bear in mind that there exists also a similar counterpart, which is a maximization formulation, where actually the goal is to maximize the positive type weights within a cluster and the negative type weights among different clusters. Okay, but let's focus on this particular formulation, on this is the formulation which is called mean disagreement correlation clustering, or mean CC for short. Okay, here are some of the well-known results about this formulation of correlation clustering. So this formulation is an NPR problem. It's particularly hard to be approximated in terms of polynomial approximation schemes, because it is an APXR problem, even for particular instances of the problem. And for general graphs, so for graphs where there is no constraint about the structure of the graph or the weights or assigned to the various edges, the best known approximation factor is logarithmic in the size of the vertices of the graph. And this algorithm is based on rounding a solution of a pretty large linear program, a program which has a number of constraints which is cubic in the size of the graph. So this is an algorithm for general weights and for general graphs, which achieves actually approximation guarantees, but it's not really feasible in terms of running time for large instances of a graph, because its running time is at least cubic in the number of vertices. So these are not really good news, right? But the good news is that a special case of mean CC is actually tractable quite easily and quite nicely. This special case arises when the graph is complete and the so-called probability constraint is met on this instance. Probability constraint is basically the constraint which is written here in the slide. So when for every pair of positive type and negative type assigned to the same edge U and V, actually the sum of these weights is equal to 1. If this is met, if this constraint is met, basically we say that the specific instance of mean CC satisfies the probability constraint. The name of probability constraint is actually self-explanatory because the sum of the weights is equal to 1, like a usual probability constraint, right? So in this case, so for these particular instances of mean CC, actually there exists a quite nice algorithm which is called the pivot algorithm, which actually works like this. So it's a randomized algorithm. It picks a node U uniformly at random from the graph. It builds a cluster composed of U and all its neighbors that are similar, where similar basically means such that all its neighbors, all the neighbors of V of U, such that the positive type weight WUV is more than the negative type weight WUV. So the node U just sampled along all its neighbors that meet this constraint form a cluster. This cluster is removed from the graph, and then the algorithm repeat the same process again until the graph has become empty. So this is an algorithm that is rather easy. It's also easy to implement. It achieves approximation guarantee, constant factor approximation guarantee, in particular a factor 5 approximation guarantee, and it runs in linear time in the number of edges of the graph. So it is really a nice algorithm. It is an algorithm that hopefully, so ideally, we would like to have it used in general for every instance of correlation clustering. Unfortunately, this algorithm actually achieves approximation guarantees only if the probability constraint is met. While, just as a recap in this slide, for general graphs and general weights, so for graphs where not necessarily the probability constraint is met, the only algorithm which achieves approximation guarantees is the very slow linear programming plus rounding algorithm, which achieves okay approximation guarantees, but it's really slow. Its running time, as said, is cubic in the number of vertices. So now at this point, okay, the main questions that motivated our work about correlation clustering with global weight bounds is whether probability constraint aware approximation algorithms like the pivot algorithm I just described can still achieve guarantees even if the probability constraint is not met. So actually, we provided an answer, a positive answer to these questions. In particular, we came up in our ECML PKDD paper of 2021 with a sufficient global condition which somehow establishes when any algorithm that achieves a certain approximation guarantees under the probability constraint can keep the very same approximation guarantee on an input that not necessarily meets the probability constraint, but still satisfies this sufficient global condition. This sufficient global condition is called global weight bound, or GWB for short. And unlike the probability constraint, is required to hold by considering all the weights all together. So it's not it's a global condition in the sense that it's not a local condition that needs to be met locally for every pair of weights like the probability constraint, but it's a global condition that needs to hold for all the weights all together. We are going to see how and why this. And in general, because it's a global condition, it's not local, it's also a milder condition than the probability constraint. So it's more likely to be satisfied. In this way, actually, we can extend the range of applicability of the constant factor approximation guarantees of algorithms like pivot and extend the range beyond the probability constraint. So even mean correlation clustering, mean disagreement correlation clustering instances, which don't meet the probability constraint but meet this global weight bound condition, still achieves the same approximation guarantee achieved by the algorithm in presence of the probability constraint. So this actually extends the range of applicability of the theoretical guarantees of the algorithms for mean CC. Okay, this is the main contribution, and actually let's see some technical detail in order for you to understand how this global condition is defined. I will skip, of course, the proofs, but I will give you just some mathematical detail in order to have for you to have the picture more clear. So actually, the global weight bound condition is this one. So basically, if we take the average of overall the positive type weights and the average overall the negative type weights, the sum of these two averages needs to be no less than the maximum difference between any two positive type and negative type weight in absolute, okay, the absolute value of this difference. If this condition, so this is a pretty simple condition. We derive this condition by doing some mathematics, some math about reasoning about the weights and the probability constraint. It's actually not really complex math, but there are a few steps in the proof that I will skip, of course. So what's the idea to exploit this condition? So basically, if this condition is satisfied, what we can do is the following. Given the original graph, G, where again, this global weight bound condition is satisfied, we can actually construct another graph, G prime, in linear time and linear space, basically by modifying these weights, by redefining the original weights on G, redefine these weights by computing some tau weights, where the probability constraint is now met on these tau weights. Now, given that the probability constraint is met in this new G prime instance, we can actually cluster this graph with, for instance, the pivot algorithm or any probability constraint aware algorithm and achieve approximation guarantee. Well, the results that we prove in our paper is that the result, the constant factor, or not necessarily constant, the approximation guarantee achieved on this G prime is actually carries over to the original problem instance of mean correlation clustering. Okay, so basically what is written here in the slide, an alpha approximate clustering on G prime is also an alpha approximate clustering on the original G2. So the way how to actually exploit this this result, this theoretical result, is the very simple algorithm that is described, that is reported here in the slide. So basically, we have an original graph G with non-negative weights W plus and W minus, and an algorithm A which achieves alpha approximation guarantee for the given instance of correlation of mean disagreement correlation clustering where the probability constraint holds. So what we do actually is, first of all, we choose these two real numbers, m and gamma, which are needed to define actually the weights, the new weights tau, okay, according to this equation here. So I will not enter into detail of these equations, but it's, I mean, it's based on simple math, okay? And we need to pick basically any two real numbers, m and gamma, in order to actually define these new tau weights. And the results is independent on how we pick actually the m and gamma. But the important thing is that m and gamma needs to be picked such that the ratio between them is within this range. Okay, delta max and AVG plus AVG minus, where AVG plus again is the average of overall the positive type weights, and AVG minus is the average over all the negative type weights. Okay, and delta max is the maximum difference in absolute, the absolute value of the maximum difference among two positive type and negative type weights. So here we can see why actually we need this condition. So this way how to choose m and gamma is a motivation on how we need this condition. Well, because basically we need this condition because for this range to actually exist, right? Because if the sum of AVG plus and AVG minus is less than delta max, right, then this range doesn't exist. So we have no way to choose a ratio m divided by gamma which belongs to this range, because actually this range doesn't exist. Okay, and that's why we need this condition, this global condition, basically. Okay. Okay, once we've chosen m and gamma, we can compute the new tau weights on the new G prime, the instance of the problem according to this equation, which is something really simple. And then we can cluster the new G prime with the given algorithm which achieves alpha approximation guarantee on it. And then we are sure by our theoretical results that the approximation, the clustering returned by running this algorithm on the new G prime instance, it's actually an alpha approximation guarantee clustering also for the original instance of the problem. Okay. Okay, so this way we actually have extended the range of validity of application of the theoretical results of correlation clustering in presence of probability constraint. There are also practical benefits of our results, apart from extending this validity, this range of validity, which is an application to feature selection for fair clustering, which is something that we hopefully will cover in the last part of the talk. There are theoretical benefits, of course, because we can, for instance, exploit these theoretical results in other results that are built on top of the ones achieved by mean disagreement correlation clustering. And in general, we think that this is good, also beneficial in general for the research community, because this is a kind of brand new line of research, because nobody has focused on global bounds on correlation clustering, but the focus has always been on local bounds, on bounds that hold in isolation for every pair of weights assigned to each edge. Not only the probability constraints, there are other types of constraint that have been studied in the context of correlation clustering, but they are all local constraint. None of them is global like ours. So we believe that this could be a good direction in order to do also future work to reason about this global way of thinking about constraints in order to improve the current theory about correlation clustering. Okay, here are some experiments that I think I can times it. I can skip just to give you an idea where we performed some experiments in order to see actually when the global weight bound is satisfied. We actually checked that the results of pivot run on these instances, and when at the same time the probability constraint is not satisfied, actually achieves results that are in line with the approximation factor that actually holds in theory. So, and it's actually the case, and we actually verified this also by comparing the pivot algorithm with the linear programming algorithm, and we observed that whenever the problem instance satisfies the global weight condition, the global weight bound condition, actually the quality of a clustering computed by pivot, by the pivot algorithm, is actually close to the, or better to the clustering computed by the linear programming algorithm. Okay, here are also some running times where, of course, we show that pivot is much faster than the linear programming algorithm, and that's it, I think, for this topic. Okay, this was okay, a way how to extend basically the range of validity of application of practical algorithms for correlation clustering. In this second topic, in the second advance about correlation clustering, we actually provide a reinforcement learning formulation, where the first reinforcement learning formulation of correlation clustering. So these are the main contributions of this line of work, where we actually provide a sound formulation of correlation clustering in a reinforcement learning setting, and in particular in a specific framework, reinforcement learning framework, which is called combinatorial multi-armed bandit framework. We design some algorithms for this formulation, and we theoretically analyze the algorithms. We provide some approximation guarantees for this algorithm, and we provide also some experimental evaluation. So let's see this formulation. Okay, this is again a formulation of correlation clustering, the mean disagreement formulation clustering, mean disagreement formulation of correlation clustering. Where the goal is to find a cluster which minimizes as much as possible the sum of the negative types within a cluster and the sum of positive types among nodes in different clusters. Okay, what is the context of defining, what is the reason of defining our reinforcement learning framework for correlation clustering? Well, the idea is that, okay, in usually in correlation clustering, weights are assumed to be given up front, right? So the user provides these weights, and then the goal is to perform this clustering. But in general, these weights in some contexts, several contexts, are not necessarily noun, or at least their final form of these weights is not noun. In several contexts, maybe one can start with initial guesses for these weights, and then it will be desirable to discover these weights while the various clusterings, the various correlation clusterings are actually placed, and a feedback from these clusterings is exploited in order to update the knowledge about the true weights. Well, this is actually exactly the context where we focus on. We focus for the first time on a correlation clustering setting where the edge weights are not available, okay? And edge weight assessment is carried out while performing clustering, basically, okay? These are several applications, team formation, recommendation in online social platforms, task allocation, so on and so forth. So in the paper, we describe all these applications in detail. So let me just give you some idea about the first one, the team formation application. So for instance, if you want to cluster, if you want to form teams so as to, in a way that you cluster some individuals in teams that perform in such a way that they perform well for a given task, you can actually, okay, you at the very beginning you don't know how to compute similarity of any two individuals in terms of how well they will perform if they are put in the same team or not. So at the beginning, you can start guessing these weights according to, I don't know, skill-based similarity measure. So you can put any two individuals in the same team if they somehow share the same skills. But this doesn't consider, for instance, human factors. So, for instance, if they are compatible, basically to work in a team. So this is something that you can really just only observe whenever you put people, individual, in the same team. So whenever you actually place a cluster and you observe a feedback from this cluster. And this is exactly the context of correlation clustering with unknown weights. So you can compute an initial clustering by some initial guesses of these weights, based, for instance, on the skills shared by any two individuals. And then you can start placing these teams. You can observe how people perform actually if they are put in the same team or not, and you can update, you can exploit this feedback to update the weights, the original weights. And then you can perform another clustering in a future instance, which exploits the new weights that are based on the previous feedback, and so on and so forth for several rounds until you get actually a guessing, no, not a guessing of the weights, but the actual weights that are actually effective enough in order to perform an effective correlation cluster. Okay, so let me give you some details on the framework that we actually defined here. Okay, we actually modeled the intra-cluster. So in correlation clustering, we have a positive type weight and a negative type weight assigned to each edge. We model these two weights as two random variables, okay, with some mean, which is denoted by mu. And both the random variables, both the distribution, the whole distribution of the random variables and the mean are unknown. Okay. So the idea is that, okay, we start at every time, actually, we keep just the estimates of the mean of these random variables that models the various weights, and we place a clustering according to correlation clustering by using what we call an oracle, which is something which is just an algorithm to compute a correlation clustering, given the way the estimates of the current estimates of the mean. Okay, whenever we place this clustering, we compute actually this clustering according to the current estimates. We can observe this clustering, and we can get a feedback in order to update back the estimates of the mean of the random variables. How do we do that? Actually, we interpret the weight of any edge within a cluster as a sample of the negative type of the distribution of the negative type random variable, while the weight on an edge between two vertices which are placed in different clusters is interpreted as a sample of the distribution of the positive type random variable. Why this? Because you remember, in correlation clustering, we minimize the sum of negative intra-cluster weights and the sum of positive inter-cluster weights, right? So if we got this certain clustering, we actually can assume that the intra-cluster edges somehow are a good estimation of the negative type random variable, because the negative type weight is minimized in terms of intra-cluster, in an intra-cluster perspective. And the opposite happens for the intercluster weights. Okay. Okay, what do we want to minimize, to optimize in terms of optimization problem? Where actually we want to optimize the sum of the various correlation clustering objective function value over all the rounds of this process, because this process is repeated for a fixed number of rounds. So the idea is that this is pretty important, because the idea is not just to get to a good clustering at the last step of the process, so at the step which is denoted as capital T, but it's important that the clusterings that are achieved along the way, during the way, are not so bad, because otherwise at every round maybe I will compute clustering which is really bad, and it's not good, because this is something that's actually exploited also in the intermediate rounds. You remember, in the team formation application, we actually exploit the various teams computed at the various steps. But the most important thing is that going on, actually, we improve in the clustering, we improve in the mean estimates, in the weight estimates, and we get to a clustering that is good enough. Okay, how do we do that? How do we actually try to improve this clustering along the way? Well, basically, typically in a reinforcement learning scenario, you have this exploitation-exploration trade-off. So exploitation means that you actually perform a clustering, a correlation clustering, by only considering the current estimates of the mean of the unknown random variables. On the other hand, exploration means that you try to explore something that is different. So you actually try to perform clustering by somehow deviating from the current knowledge, from the current estimates. Both the exploitation and the exploration are good and bad for different aspects, right? Because if you exploit, you are sure that okay, at least you stay close to some knowledge that you have already acquired. But if you don't explore, actually you are not sure. You cannot be sure that something that you have not some knowledge, the knowledge that you have not acquired is perhaps better than the one that you already have. So typically in a reinforcement learning scenario, you want a trade-off between these two aspects. And this is something that actually we do by contextualizing correlation clustering in a combinatorial multi-armed bandit framework. Okay, this is a framework, a specific reinforcement learning framework. I will give you just some hints about this framework, and then because formulating correlation clustering in terms of this framework is not so difficult, so it's not the main contribution of this work. So actually in this framework you have a set of M-base arms, which are basically slot machines, can be depicted as slot machines. Every arm is assigned a set of random variables, where each random variable denotes the random outcome of playing this base arm in a certain round. At each step, basically an algorithm, an agent which plays this game, let's say game, we select a subset of these base arms, okay, which is called a superarm. Playing this superarm actually gives a reward, which is assigned to every possible superarm, and it's again a random variable. And it is assumed an availability of a so-called alpha-beta approximation oracle for choosing actually the superarm to be played, okay, which is an oracle that is for which the reward, the probability that the reward of playing the current arm, the probability that the reward of playing the current arm is no less than alpha, the reward, the expected reward of playing the best arms is no less than beta. Okay. And the goal of the whole game is actually play a set of superarms in the various rounds in order to maximize the cumulative reward achieved on each round. Okay. So this is in general the CMAB framework. We can contextualize mean correlation clustering as a CMAB instance by defining actually base arms as edges, actually as a replica of an edge, one assigned to the positive type weight and one assigned to the negative type weight. The superarm is actually corresponds actually to a clustering, which is a set of base arms which actually meet the constraints that make it a good clustering. And the base arm outcome is basically what we said before, right? For an intra-cluster base arm, basically we interpret it as a sample of the negative type random variable. And the intercluster base arm is interpreted as a sample of the positive type random variable. And the goal is to minimize the loss given actually by the correlation clustering costs, but represented in probability terms, so in terms of the random variables that are assigned to the weights. Okay, I think I will have a few minutes more, so I will give you just some idea of the algorithms used in this context. So basically, our contribution here is to define algorithms for a minimization version of CMAB, because the algorithms known before this work were actually all based on a maximization formulation of CMAB. We define an algorithm, a minimization counterpart of these algorithms, and we actually prove that this minimization version of variant of this algorithm of one of the well-known algorithms actually achieves approximation guarantees in terms of what is called regret, which is a measure that actually computes how good the clusterings over all the rounds are in terms of the objective function of the underlying optimization problem, which in this case is mean disagreement correlation clustering. And actually, we proved that the approximation, the regret achieved by the algorithm that we defined is logarithmic in the number of rounds. Okay, I will skip these details where there are a bunch of experiments in the paper to prove the accuracy, the effectiveness, and the efficiency of these algorithms for CMAB. I think I will skip this just a couple of minutes in order to introduce the third topic, to give you just an idea of the third topic on how actually correlation clustering can be contextualized to the context of fair clustering. So in a context of fair clustering, actually the goal is not, in standard clustering, the goal is to group similar objects within the same cluster, right? In a fair clustering context, this goal is coupled with the goal also of having objects of a particular sensitive type well distributed across clusters. Okay, so basically we don't want cluster dominated by a specific type of sensitive data class. For instance, people having the same race, the same gender, and so on and so forth. Okay, this a fair clustering can be actually modeled as a correlation clustering. So whenever we have a data set like these ones, for instance, where there are attributes that are non-sensitive and attributes that are sensitive, one can define similarity between any two objects in terms of the non-sensitive attributes only to derive a positive type weight. And the negative, a similarity between the sensitive attributes can be used to model a negative type weight. And then we can cluster these objects in a correlation clustering style. Okay. The idea is that, okay, non-sensitive attributes are going to be minimized within, so the similarity between the similarity among the intra-cluster weights will be actually maximized in terms of non-sensitive attributes. And the other way around, the opposite happens for the sensitive attributes. Okay, and this is what actually we do in this paper that we published in the Discovery Science Conference in 2022. where we actually defined a correlation clustering instance based on this definition, and we performed experiments in order to observe how and why this particular formulation of fair correlation, of fair clustering in terms of correlation clustering behave compared to the state of the art. And we actually observed that, okay, I will not give you the details of the experimental results, but let me just say that this particular formulation actually achieves results that are comparable to the best existing methods in the state of the art. So this is a promising direction for research, because what we did here was pretty simple, and it can be actually extended and defined in a much more sophisticated way. So it's really something that that is worth to be pursued in future work. Okay, I think that's it from my side. I think we can stop here just to have some time for questions. There are any questions?
Okay, I think question from Michael.
Yeah, so this is really interesting. Great talk. I was wondering, do you know, has anyone tried using GNN approaches for these problems?
I'm not aware of that. I think not, but yeah, I actually don't really know. But I think no. Yeah, yes, there's no GNN approach for this particular formulation. No. Of clustering, no. I mean, there are GNN approaches for clustering in general, but not for this particular formulation, for correlation clustering, I think. I'm not 100% sure, but I think not, yeah.
Okay, and then just as a follow-up question, so I know this would be slower than the methods you're talking about, but if someone tried to use a spectral clustering method using like signed versions of the graph Laplacian, where you're trying to like do the max cut, but you're trying to keep enemy nodes apart from each other, how would the results of your method compare to that?
Well, but that's a different formulation, right, of clustering somehow. Well, I don't know, in the sense that we don't compare our formulation with different formulation. So this correlation clustering formulation with different correlation clustering, with different formulations of clustering. But actually, this is something that is perhaps worth to be investigated more, because yes, this is something that is actually worth, yeah.